Okay, everyone. Stations, please. Okay, welcome to session number 7, conceptual blending. A much talked about concept in this conference, and we will continue to talk about it a great deal in this session. And you may remember the best paper award from last night. Well, the recipient is here, and his co-author, Tarek, can't make it, so he's a regular at the conference, and you'll all know him, I think, or will soon know him. So it's my pleasure to introduce the first paper of this session, Generalize and Blend, conceptual blending based on generalization, analogy, and amalgam.
Hello. So it's a long title, but I can tell you the goal mainly is to try to elucidate the relationship between analogy and concept blending. So analogical reasoning for a long time in AI and cognitive science, we have said it's a very important part of human cognition and also in creativity. And then people now working in concept blending in the recent years, they also claim that it's a very important, maybe the most important mechanism for creating new concepts and so on. So we wanted to study the relationship between the two, and we are able to do that and make a proposal for an answer based on two intermediate notions, which will be generalization and amalgam. So the project COINVENT, in which we are working, takes the concept blending as the core of the concept invention machinery, so to say. In addition to that, we also said we wanted to study analogy. And what I'm going to do at the beginning is to have a rather abstract presentation of these notions, but later we will have two examples that I think will help to ground these notions. So, conceptual blending, probably most of you know about it, but the generic idea or the general idea is that you have two input spaces that they are called sometimes concepts, sometimes mental spaces. We have been discussing about that in this conference here. Then, I don't know why it makes this noise every time. Anyway, then there's the generic space in which you represent. I cannot do it. I think let's try like this. Okay. Anyway, I will point. So the generic space, the intuition about that is that you represent in here what is common to these two spaces in there.
There's one on here too.
Yeah, but
it won't advance your slide.
I have to now.
Don't press the other button.
I have to now. Okay. So the idea of the generic space is that in here you represent what you have in common in both input spaces. And then the blend is a composition of part of the information you have here and part of the information you have here. They call them projection. But the important thing that we will see gives some problems later to develop a formal model and a computational model of blending, which is what the project intends to do, is this partiality here. So one famous example is the houseboat. You have some representation of house, some representation of boat. The generic space represents what is the commonalities between the two, and from there you can generate different blends. One of them is the houseboat. And the next idea would be, okay, if we have this generic, this schema, and we want to see what relation we have with analogy, they don't look very similar. I mean, we have some generalization above, but that's about it. In analogy, we have a source and a target, and the idea is that we want to move as much information from source to target, which typically target is a poorer theory, the typical example is we know about the solar system, and we want to map information about the solar system into our model of the atom, so we understand better the atom. So how these two are related to each other. So the point where we started in the project is by Gauguin's model of concept blending that he used category theory. However, the problem here is the partiality in this morphism here gives a lot of complex technicalities in category theory, and he had to use a very complex category theory. And that gives us problems. First of all, we also want to have a computational model, and in 3.5 categories, this is not known. Whoop, that's too fast. Oh, yeah. Okay. That's it. Okay, then the idea we introduced here is come from the notion of amalgam. That's something we developed in case-based reasoning. So in case-based reasoning, the idea is that you solve a new problem using an old problem that's already been solved in your case base. However, sometimes you want to use more than one of these cases. So you want to combine two of these cases, and then use this combination to solve the new problem. And that's what we call amalgam here, and we will explain later. In the idea of amalgam, we are using the basic idea of generalization that we can use here to model partiality. So we have these two inputs, okay? But the correspondence or the mapping from here to here is partial. So one way to represent that is to have an intermediate object, which is a generalization of the input, to have another intermediate object that is a generalization of the input, and then from these two, to have a blend. Of course, we have a lot of possibilities because we can generalize this in a lot of ways, right? Every time we generalize, we preserve some properties, some information, and we discard others. How we do that, or all the models in which, the ways in which we can do that give us a lot of possibilities here, and then different blends. And then in here, I'm changing the order to have the intuition of the vertical axis here, that what it's above is more general than what is below. So it changes from the classical one. So we have the generic space, which is what's common between the two inputs. The two inputs are generalized. For any couple of these generalizations, we can compute the blend. Okay, in order to do that, I will present now the notion of amalgam. It's a quite general notion. You can work in any language in which you have a clear idea or a clear representation of what's a subsumption between your descriptions. Subsumption here means more general than. Anybody has any problem with the idea of one formula being more general than another, or one theory being more general than another? That's only everything we need. Okay, once we have this idea of subsumption, that means we have a generic description in here that is that comes from the two inputs, two generalizations of the inputs, and then the combination of these two. The generic space, basically in this approach, is the least general generalization or anti-unification. That's the generalization that are common to both inputs, the more specific one. That means that you have what is shared between the two inputs, and you have all that is shared. And then the second part is that there's the dual notion of anti-unification, that is unification, when you put together two descriptions into one. The only difference is that here, what we put together and what we call the amalgam are not the inputs, but the generalizations of the inputs. You can think about that as a kind of partial unification. So we have two descriptions. We would like to put them together, and we can. We have to renounce some properties, some parts of it in each one of the sides. So we can do it in several ways. Each of the several ways is one generalization, and for each pair of generalizations, we can, if they have a unifier, then we have an amalgam. Okay, so the one on the top, the generic space, let's say, it's the anti-unification or least general generalization. And the amalgam, which is putting together these two generalizations, is the unification or more general specialization. Now, the claim here, let's say, is that analogy can be seen as an asymmetric amalgam. That is to say, now the two inputs are considered not equal. They are considered asymmetrically. One is the source, that we assume we have a lot of information. We have the target, in which we have less information. We cannot put all the content that we have here directly into the target. We have to generalize this one. And we want to generalize as little as possible so that we can already unify with the target, so that we can transport or transfer as much information from the source to the target as it is possible without an inconsistency. So this is the anti-unification again. And then what we are calling here the result of the analogy would be an asymmetric amalgam, which is the unification of the generalization of the source and the target. So you see, it's not so far away from the original idea of generalization. It's just that in here we're talking about the source, but we are not talking about which part of the source we are really going to map into the target. And we talk about the target, but we don't distinguish between the target before making the analogical inference or after enriching the target with all the analogical inference that we have performed, what we have transferred from here to there. And now we are going to have a couple of examples. I took this example from another paper, so it's not one of my examples. This is from a paper called Ontology Blending. So they were working with concepts represented as ontologies. Our idea here is that the mental spaces of the input should be represented something like image schemas or typical instances of categories. So if we talk about forest, and forest has trees, and if we don't say anything else, we know from natural categories that people tend to have a typical or prototypical or stereotypical, I don't know what you want to call it, image of a tree, and then a forest is a bunch of trees. Also in traffic signs, there are a lot of different shapes and forms, but there's one which, let's say, is the canonical or the one you think about. Like when you say pet, you think about cats and dogs and not snakes. So we are going to think about how to solve this, how to create this blend, where the input is this idea of having a stereotypical representation of the concepts being mentioned, which is the traffic sign and the forest. So the sign forest here is interpreted not as forest sign, but as a group of signs that are together. And then the signpost we consider is the stereotypical traffic sign. So we represent this here in this example in feature structures. Feature structures, it's very easy to understand. We have just different objects and relations between the objects. The relations or features have some name in it, and then each one of the nodes we have a sort, and this sort can have in a hierarchy more general sorts. So a car is a vehicle, a signpost is a physical object, a tree is a plant. So you can see already that they have certain similarities. They are in different domains, so one is about biology, the other is about science in traffic. So, but you have here a post that is fixed to the ground with something above, which is a panel that displays information. On the other hand, we have a forest, which we just say it's a group of trees, and trees is a typical tree. It has a trunk. No, not all trees have trunks, but this is a typical tree. So you have a trunk, a crown, and a root, which is the mechanism that fixes you to the ground. Okay. Now we can see if we do the anti-unification here, what they have in common is more or less what we glimpsed at the image before. It's a kind of vertical stick that is fixed to the ground and is supporting something above. This is what they have in common. So now in here, we can apply the schema of blending, and we will see that in fact it's an asymmetric blending and thus an analogy. So in this case, this will be the target because the signpost we don't need to generalize. In fact, it's the same. However, the generalization of the forest, it says that it's a forest and then it's a group of something that is very generic. It's in fact the generic space that we find there. And then what we do is unification of these two. This, which is a generalization of this one, and this that it's identical to this one, so it's asymmetric. And then we have a forest that is a group of signposts that has a panel, a post is fixed to the ground, and the panel has information. So we have created the blend, which is, let me see, which is the idea of the forest of signs. Why it makes sense to talk about a forest of signs and not a forest of chairs, for instance? I mean, chairs are typically made of wood, and trees are typically made of wood. But this is like one property they have in common. However, in here we have some structure that is very perceptual that links these two different objects from different domains to one to another. So our hypothesis is that this kind of analogy, or maybe metaphor, it makes sense when you have a strong network in here that relates both. In order to check whether this intuition makes any sense or has any validation, what we did was using Google's Ngrams database to search for existing phrases in which there is the word forest of something. We eliminated everything except the ones that use this forest of metaphorically, and we find, in addition to forest of signs that also appears, we have forest of spears, forest of masts, a forest of marble columns. Both masts and columns, they are fixed to the ground. Spears, they are not fixed to the ground, but maybe you think about, I don't know, Spartan warriors in formation with the spear in which they not move. So it's not so different from the ones we had. Interestingly, we also found other metaphorical uses of forest of X, but the kind of metaphor they were using was different. Was 5 minutes?
Yeah, let's say 5 minutes.
No, it's only 20. Okay. But okay. But it's a forest of opinions, possibilities, desires, words, human experience. So it's like another kind of metaphor, like you in a forest in which you have a lot of possibilities and you have certain So the other example comes from HDTP that's developed in Osnabrück. It's a heuristic-driven theory projection system that basically is of the family of structure mapping engines for analogy. So what they do is the mapping between the source and the target is performed by aligning pairs of formula. So each of the inputs is a set of is a theory described by a set of axioms. And then the anti-unification that can be of a restricted higher order is the one that finds the generic space. So I have to run, but basically what they do to compute the generic space is this part on the left. They compute here the variable substitutions that go from the generic space to the source and the target. And then we will use these mappings here and here to build the final analogy. The example we are going to use is this foldable brush. And it's easy to see that the inputs are a pocket knife that can be folded, a toothbrush, and we want to obtain the blend there. So the general idea is to work like that. We will have to find first we will build the generic space, then we will generalize that, the source, and then we will put together these two. So the stereotypical characterization of a pocket knife is very easy. It has three parts: the handle, the blade, and the hinge, and two functionalities. It can cut, it can fold. The toothbrush has two parts, which is the handle and the head, and has one functionality, which is brush. So first we compute the shared generalization. Okay. So this axiom corresponds to the other one, so we can generalize here in a variable E that has something which is a part which is a handle. Then we have the second part that corresponds to the other one, but now it's some generic part P, we don't know which one. And on the left, the system keeps the substitutions from the variables for each one of the inputs. This one has no counterpart on the other side, so we don't do nothing. Then we have the functionality, which is cut and brush. So we have some functionality in here, and then we have this functionality, this second functionality here, that we cannot put because it's in there because it's not common. Okay, now what we're going to do is to generalize the source theory. Okay, this is already part of the source theory because it's in both. So now we need to generalize this. In order to generalize this, we look at the substitutions, and we can substitute pocket knife by the variable E, and then here as well. So this is the generalized source theory. And now we want to combine this with the target. So this is the target. And this has two parts because of some technicalities that are part of the system. So first we build what is called the proto blend, and then the final blend applying the substitutions. So in here first, we have that this will be unified with the part of the toothbrush, which is this one. So we have a toothbrush with a handle. The second one is another part that in this case is the head. We have the functionality that is this one. And then we have this other information that in fact comes from the source, and it's not in the target. But applying the substitutions here, we can compute the final blend. So E will be the toothbrush, of course, and the functionality also will be the toothbrush. And so this is the final blend, which is the image we saw at the beginning. So, to summarize, we had the original idea of blending. We had the modeling of the partiality of these projections from the inputs to the blends represented by these intermediate generalizations. This comes from the idea of amalgams. And then the notion of analogy can be captured by this idea of asymmetric analogy, in which the target is not generalized, but the source is generalized as little as possible, so we can transfer as much as we can. Now the thing is, this is related in some way to classical considerations of analogy. So there are two basic schools here. One is the similarity-based analogy. Says if the source is similar to the target, and from S we can derive A, we can conclude that alpha will also be the case in the target, right? And the transfer we make is we try to move all the alphas we can from one to the other. But this is the classical logical formulation. The other one is, instead of calculating a degree of similarity, for instance, is a generalization-based or inductive analogy that considers analogy as a kind of induction, that instead of trying to find a description of the whole class, you're trying just to have the scope of the source and the target. So in here, if these two are similar, and in S is the case that alpha is true, then we take what they have in common, which is that unification, and then we assume that this could be derived not from all of S, but all of S, but just with this part, it could also be derived. We don't know, of course. That's why it's a kind of non-monotonic reasoning. And then after we have this, then we can conclude that alpha will also be the case in T. And this is the final slide. If you can see, this is not so different from here. So we have S and T. We have the anti-unification in here. And the alpha in here is the idea that you can infer a new property on the target. In here, the idea is that you want to find as many properties in S prime that you can preserve from S that you can push into the final blend or final amalgam so that it's consistent with the target. Okay, thank you.
Okay, I anticipate a force of opinions and a barrage of questions in 4 minutes. Who's first? Ollie.
Okay, so just for the toothbrush thing process, how do you avoid producing cutting toothbrush? So in which part of the process you will kind of discard the cutting and select the hinge and the folding? That's reason it out.
You discard the folding set. Yeah, you can have all these different possibilities. This is the problem of all the possible blends that you can do.
Okay.
And how you select from all blends or blendoids, which is the one that you want. Yeah.
So it should be kind of defined before that we are trying to have something like folding toothbrush, and based on that it can select the folding.
No. What I'm saying is that you can get this blend, and you can get a lot of other blends.
Okay.
People in conceptual blending, they are aware of that, and they apply something they call optimizing criteria. We don't know where they come from. I mean, they come from the human mind, but if we want to make a computational model of that, it's open to discussion.
It generates many possibilities, and
yes.
The author will select what is the best.
Well, in here we are not talking about how you use that in a system. We are just saying that we can reconstruct that in this way. But in the last talk today, it's about designing computer icons, and in there we talk about how we can discuss the possible outcomes and why one outcome is better than another one, which addresses your concerns.
Geraint?
So, related question, if I may. So, the first thing that really struck me with your toothbrush example is that if you'd done the mapping the other way around, right, with the has part thing, then it would have been completely useless. And I mean, I realise that you're not claiming that it wouldn't be, so that's fine. But the obvious thing there is that you could look at typical knives, and you could work out from that what's the interesting thing about the pocket knife. Right? So maybe there's the basis for some interesting things there, and I wonder if you have a theoretical take on that. And the second question is the one that I always like to ask when people talk about this kind of representation, which is that what you have here is essentially a network representation, and the operation system is fundamentally dependent on the representation that you're using in the network. Now, how do you get around the problem when these things don't quite match up? Like, so if I was doing this in RDF, let's say, and I wanted to have semantic web technologies going, and my two ontologies don't quite match up, then it won't work, right?
Yeah, no, I totally agree. I mean, this is the kind of the basic problem where the two inputs mental spaces come from. I mean, if you have the house, not my example, the typical house boat example. Why there's no insurance in the boat? Why is no insurance in the house? If you have a house or a boat, you probably have an insurance, but it's not there. So how you represent things, it's a very important thing in artificial intelligence. That from the logic, I think the logic-oriented AI has focused more on inference than on representation. So this is a problem in AI in general. In here, our idea is to try to focus on the idea of image schemas, so that it would be cognitively plausible that certain representations are preferred to others, but this is ongoing work.
I was struck by the fact you didn't represent why the knife has a hinge or why it's useful, which would be a key part in putting a hinge into a toothbrush. You wouldn't just put a hinge into a toothbrush because you saw one in the knife. You put a hinge into a toothbrush because you saw that it was very useful on the knife.
Well, the function is that you can fold. That's
Okay.
the only predicate that is related to the usefulness is the functionality. You have two functionalities, cutting and folding. In the other one, you have one functionality,
Oh, okay.
which is brushing.
If you ever watch prison movies, they often sharpen toothbrushes. Actually, Hanny was telling me about that. Okay, so since you're speaking later this afternoon, maybe further questions can be saved for the next talk. You'll be talking about blending again.
Yes.
So
I'm afraid so.
no, that we look forward to it. So perhaps Ash, I think it's safe a question for the
Talks are about
next talk.
blending.
Thank you very much.